Hi everyone, and welcome to a new interview. In today's episode that we recorded in the early half of July 2023, I'm talking to Shai Machnes. Shai is the CEO of Qruise, and we're going to partially focus on the work that they're doing with that company. We're also going to focus on the intersection between quantum computing and machine learning. So the intersection between these two fields is where Shai is focusing his research, and we're going to talk about upcoming technologies on the machine learning side and how they extend to quantum computing architectures. So let's get started with that discussion. Hey Shai, thanks for joining.
My pleasure.
Today I figured we could kick this discussion off by talking about a concept that you've articulated in the past, namely an AI physicist. So you're working in the intersection, I guess you could say, between machine learning and quantum computing. And there's a concept that you've not necessarily coined, but at least stated about AI physicists. So I would just like to pick your brain a little bit on what you think about when you say that concept, what the ambition is over the long term of how we can integrate machine learning with quantum computing in general.
Right. So you can do it in one of two ways at the moment. Well, at the moment, there's one way. There'll probably be two others going forward. So right now, quantum computers aren't very good. So what you can do is you can use machine learning to help improve and design quantum computers, which is what our company does. Once we get better quantum computers, one can use quantum computers to do machine learning. And one of the machine learning things you can do on future quantum computers is improve quantum computers. Right? So if today to do what Qruise does, you need to classically simulate quantum devices, in the future you could do the simulation on another quantum device. Mm-hmm. So it would be like a bootstrapping process. Just like, people are now using output from ChatGPT to train other machine learning models. Mm-hmm. But right now, quantum computers aren't very useful yet. They're mostly, I would categorize them as engineering prototypes, meaning they're good enough for physicists, engineers to learn how to build quantum computers, how to use them, etc. Mm-hmm. And, or maybe even the wider, potential users and things like that. But you can't run anything useful on a quantum computer that you won't rather run on a classical computer. Not yet. Mm-hmm. So for now, doing classical machine learning to help improve quantum computers is what we do.
Mm-hmm. Okay.
But also other types of devices like quantum sensors. And it's a pretty general field.
Mm-hmm. Before we focus on that in more detail, let's maybe talk about the other approach first. So you mentioned this sort of cyclical behavior and how you can make these enhancements. Is the key reason why you would want to use quantum computers to then enhance your quantum computers in the end that you have a much more natural overlap in terms of the physics associated with them? Is that the key?
So the thing quantum computers will do best is simulate quantum physics. Mm-hmm. Because let's say the memory requirements for simulating quantum physics is kind of exponential in the number of qubits or degrees of freedom, let's say, of the quantum system, which is partly why, for example, we don't fully understand high temperature superconductors and we don't have room temperature superconductors yet, because these are kind of deeply quantum materials. And even if we can write down the equations for, one atom and one electron and how they interact, in these materials, you have a large number of electrons interacting with a large number of atoms, and we simply can't solve these equations, not analytically, but not even numerically. Quantum computers should be able to do that pretty directly because it's a natural fit. Mm-hmm. But as I mentioned, not quite yet.
Right. Besides the, let's say, specific material considerations that quantum computers might help simulate? Are there general, so I don't want to get into the details of Qruise yet, but this sort of comes into like almost to the domain of Qruise. When you think about optimizing a quantum system, a lot of the developments that need to happen, as I understand, with especially superconducting circuits, is you want to construct better models of your quantum device. Is the bottleneck there right now that you're not able to simulate quantum-like systems well enough, or is it some other bottleneck? I'm thinking, like, to what extent having quantum computers in this space actually helps resolve those kinds of problems?
So the problems we're having with quantum are not, how will I say, they are about quantum, but also you can contextualize them in a bigger framework. When you're developing physical devices that are really at the cutting edge, you don't fully understand what's going on in there. So there is something that's called the forward problem in engineering, which is creating a accurate simulation of something, so that if you did your simulation right and you didn't mess up the construction, the device will behave as indicated by the simulation. Okay. And there are fields of engineering where this works great, right? If you design a house in the appropriate software and you compute the stresses and the loads and everything, and you don't kind of cheat on the materials when you actually build it, it'll be stable, just like the simulation predicted. And there are other fields where, let's say, electric motors, right? The technology is quite well understood. So I can simulate an electric motor in detail, and what the simulation indicates would be the performance, very likely will actually be the performance in practice. But there are technologies where this is not the case. For example, quantum technologies, but not only. For example, let's say silicon photonics. So there are chips that have kind of photonic pathways that are fabricated kind of generally in the same kind of lithographic approaches as you would make chips. But humanity in 2023 cannot control the optical length of these pathways to sufficient accuracy. Because for the system to behave the way we want it to, we need to control the kind of the lengths of these things to within a small fraction of a wavelength. And we don't know how to do that yet. So you fabricate the device, but the phase difference between the two kind of pathways is kind of random. Why? Because we don't have sufficiently good manufacturing control. And therefore you need, like, once the device comes out of manufacturing, you need per device to actually measure what's going on and make corrections. And in quantum, it's partially that. We have, let's say, in superconducting qubits, at kind of at the bottom of the qubit is a very small, super sensitive component that's based on quantum tunneling, known as the Josephson junction. Quantum tunneling has kind of exponential sensitivity to kind of changes in distance and potential and other things. So, a few atoms move to the left or to the right, and now this thing behaves differently. We don't know how to make things at atomic accuracy. Right? Humanity hasn't figured that out yet. So we make qubits, and they don't come out exactly the way we planned. But on top of that, you have other issues. So you control these qubits with electromagnetic fields from these kind of boxes of very high-end electronics that can manipulate fields at the nanosecond timescale. But like everything, nothing's perfect. So on these controls, you get, 12 bits of accuracy in the voltage, right? But the 13th qubit is randomish, but it's actually even kind of worse because the way it's random is problematic, let's say. And you need to start accounting for it and measuring exactly how much noise you have and how much crosstalk you have between all the wires. And so the distance between what you design and what you are able to fabricate, there's some gap there. And that's what limiting the performance of quantum computers. So we need tools to kind of, in some sense, reverse engineer the devices we ourselves are building, because we plan them to some accuracy, we fabricate them to the best knowledge of humanity, today, and yet that gap between what we actually get and what we plan is kind of the pain point for performance of the device. And then having tools to kind of understand in great detail what's going on. And, given, you could have, for a certain quantum operation, you could easily have between 5 and 10 different sources of noise simultaneously. And to be able to understand which of these is actually the pain point, which of these is actually the limiting factor, which tells you what you need to focus on when you're developing the next iteration of hardware. This whole thing is really, really hard. But it's not limited to quantum. In quantum computing, the equations that describe the dynamics of the system are the Schrödinger equation, variants like Lindblad equation and other. Right. But in other systems, it could be, electromagnetic waves, or propagation of light in matter, which is electromagnetic waves, but in a different frequency range. Or other things. You could have phonons, which are essentially slight vibrations that also affect things. And sometimes it's really silly things, like the 50 hertz of the electrical signal from the wall, somehow weakly propagating through all the devices and all the electronics. And it's tiny. It's like 0.1% or whatever. But when you're trying to get to 4 and 5 nines accuracy, you're trying to get a quantum operation to be 99.999 accurate.
Right.
You get like a tenth of a thousandth of a noise from somewhere. That's a problem. And that's what the field is wrestling with. And everybody's wrestling with it in different hardwares, different attempts to get there.
One thing I want to linger on for a second that struck me was you talked about Josephson junctures and the way those are being fabricated. You said that depending on where the atoms actually end up in the fabrication process, that will have quite significant effects on the actual model or the actual product that you get in the end. Is there also a time dimension to that? I'm thinking the architecture as such, or the material as such, once it has been fabricated, does that have a tendency to shift over time? Let's say, yeah. So it's not just that you need to characterize all the noises you have, right? But it's also really on the material level you have changes.
It's not just on the material level. So I'll tell you something we experienced in the last 48 hours. Okay. In the last 48 hours, we're working on this superconducting quantum computer, and the lab had a glitch in the cooling mechanism. So if the chip is usually 300th of a degree above absolute zero, it went all the way up to 1 degree above absolute zero, right? That's still a lot colder than outer space.
Right.
It's really, really cold. But it was enough that first nothing worked. And then once it takes hours to cool it down back. Atoms shifted because of this higher temperature. And where they settled wasn't exactly the same place they were previously. So things kind of worked, but the accuracy was very bad. So we had to remeasure all the qubit frequencies and all the parameters of the chip, because everything drifted, because heat it up, but heat not all the way up to room temperature, like from 0.03 above absolute zero to 1 degree above absolute zero, and that was still enough to mess things up. So these things are kind of painfully sensitive. There are other technologies, by the way, that are far less sensitive. So
would you say superconducting architectures are the most sensitive to these kinds of things, or when you say other architectures that are less sensitive, what are you referring to there?
So to kind of take the other extreme, NV centers, meaning you take nanodiamonds or artificially manufactured diamonds, and you shoot nitrogen atoms at them. Sometimes the nitrogen atom will kick out a carbon atom, and that creates like a quantum system that you can use as a qubit. It's a bit more elaborate, but generally speaking, this is valid. Now, this system is quantum at room temperature.
Right.
So you don't need to cool it at all. And for example, trapped ions, most variants don't need cooling either, but they need excellent vacuum. However, it's not that hard to build 100-qubit superconducting quantum computer, because if you know how to build 10, going from 10 to 100 is, with superconducting, it's mostly more of the same. It's an engineering challenge, not so much scientific. But with trapped ions and NV centers, others, there's kind of inherent limits that make it really hard to scale beyond a certain size. And you need to change.
Sorry for interrupting. What would you say?
Some different advantages. Some scale better, some are more sensitive, some are this, some are that. So it's not clear. That's why people are trying multiple directions, because for every technology people are working on, you can count advantages and disadvantages. And it's not clear, where we'll make the breakthrough.
Can we stay on trapped ion quantum computers for just a second, and particularly focus on the scaling up of trapped ion quantum computers compared to superconducting ones? Is your view that that would be sort of easier to do? I mean, this is all maybe in sort of parenthesis because it's hard to predict what roadblocks would potentially be ahead, but your general view of these two architectures, comparing them, would you say there are more significant roadblocks for, let's say, scaling up trapped ion quantum computers as opposed to superconducting ones? Because the reason why I'm asking this is I actually talked to someone before who was of the impression that scaling up trapped ion quantum computers could actually be quite replicable as well, because you have similar, because you circumvent some of the fabrication issues that you have with, for example, the Josephson junctures. If you take that, like the atoms that you use in a trapped ion quantum computer are identical, so that would potentially be an argument for scaling it up.
Right. So the atoms are identical, right? So but the environment in which they are held, the magnetic fields, the potentials used to control them, are not exactly identical. And we need everything to be identical.
Right.
So the other is that superconducting qubits are fabricated with, let's say, lithography type techniques, right? And we know how to make chips with 1 billion transistors today. So from that perspective, the let's say the chip part, it's a little bit easier to scale. However, if you think of trapped ions, so people used to do linear traps, which was kind of, you arrange magnetic fields so that all the ions sit in a row in one magnetic. That Rainer Blatt used to kind of spearhead that. He got to 14 qubits with a lot of effort, and then he basically stopped because you couldn't scale bigger than that with one kind of linear trap. Since then, people have come up with solutions, segmented traps or ideas, but So I'll say this: if you have a 10-qubit quantum, like superconducting quantum chip, going to 100 is more of the same. You're going to have a lot of problems with wires, and it gets a little big, and there's crosstalk. It's not trivial, but you don't need kind of a fundamental change of architecture. To get to 100 trapped ions, you need to start playing around with the architecture because you can't do it in one simple trap. So people do, there are ideas where the ions themselves move and you move them around. But then you're looking at something that, maybe a little bit like a pinball machine, but has 100 balls, and you need to be very careful with all of them, because if you lose one, the quantum state goes kind of, you open up the box and the cat either dies or meows, but it's not a quantum cat anymore.
Mm-hmm.
So in some sense, you can think of trapped ions as this kind of really nanomechanical system. So that comes with its own difficulties. That said, these systems can be very, very well isolated. So let's say, as far as I know, the records for the best single and 2-qubit gates are all in trapped ion systems. But the biggest systems are superconducting and not trapped ions.
Mm-hmm.
Now, then again, you have neutral atoms, Rydberg systems, where they can do large number of atoms, but then you have some difficulty with controlling individual atoms. You can do kind of global operations, but it's more difficult to kind of do individual gates, let's call it. Mm-hmm. And as a result, these systems are very well suited for simulation. But for, let's say, what I would call digital quantum circuits, it's a bit harder. So again, there are advantages and disadvantages to every approach. Intel is working on a quantum dots in silicon idea, which is even closer to the kind of lithographic, chip industry approach to things. Mm-hmm. But of course, there are also difficulties there. So, and I think that the largest they got is somewhere between 10 and 20.
Okay.
So the reason you have people working on so many directions and very smart people is that there's no clear winner at this point. It's right. So, today, every chip you can find with really tiny exceptions are all kind of MOSFET transistors. One technology took over the world, right?
Yeah.
We're not there in quantum. We haven't found our transistor, the thing you can replicate like 1 billion times reliably. And you have multiple labs, commercial, academic, exploring, multiple candidates and trying to come up with new candidates all the time, because all the options we have are not that great. Mm-hmm. All really, really hard to kind of push forward. Now, there's so many smart people working on this. I wouldn't be surprised if somebody figures something out and suddenly we have a leap. Mm-hmm. But on the other hand, there are also a lot of smart people working on fusion, and there are a lot of approaches to do fusion. And fusion is, 5 years away for the last 50 years. So it's extremely hard to predict. It's extremely hard.
One thought I had, and we could use this maybe to tailor the discussion a bit to machine learning as well. When you mentioned before the incident today, like with the superconducting quantum computer and the refrigerator that wasn't quite at the right temperature, are you seeing any sort of tools that go beyond just characterizing the architectures in a better way, but actually help with these kinds of everyday considerations for running these systems? I'm thinking that AI, I mean, obviously the sort of the natural thing your mind tends towards when you hear that term AI combined with quantum physics is you can use it to characterize your systems better, get sort of better performance. But in terms of helping out, like all the surrounding tasks that need to be done, are you seeing right now in the academical space that there are lots of tools popping up for those kinds of things, or is that still lagging behind a little bit?
Mm, it very much depends at which level you're looking at. So there's a lot of activity in machine learning for science in general. There's a lot of activity in machine learning for anything, meaning whatever word you want to put, there's a lot of activity there right now. But it hasn't coalesced into, kind of large, very powerful, mature software packages or something like that. If you want, let's say, simulations of quantum systems on the simpler side, you have packages like Qtip, an open source package. It's really, really good, right? But it kind of only goes so far, which is fine. There aren't really, for error mitigation, which is this idea that you have a noisy quantum computer, and if you not just run the original calculation that you wanted, but you modify it in really smart ways, and you run multiple calculations, you can kind of figure out from the various results what would the result would have been if there was no noise.
Mm-hmm.
So there's a very powerful package called Mythic to do that. There are other parts, but there's no kind of a comprehensive solution.
Okay, understood. One other development, I mean, that's been really coming along heavily is all the GPT models.
Oh yeah.
Have you seen any applications of that in the overall space that you're in? I'm thinking that to me doesn't come very naturally, like how you would actually apply a technology like that to a space like quantum computing. Perhaps I'm wrong there.
Yeah, not yet.
Right.
I mean, ChatGPT today is like, let's say, a very junior programmer.
Yeah.
So you can tell it to read the Qiskit. So Qiskit, for example, a very, very nice package from IBM, open source, to do things having to do with compilation and circuits, kind of a good collection of very useful things. You can tell ChatGPT, okay, read the documentation for Qiskit, and then implement for me, I don't know, the Shor algorithm for 7 qubits, and it'll figure out how to do that. But it's very much a junior, and when it comes to doing things that are, let's say, research level, it's not. And I don't think it'll get there anytime soon, because the way ChatGPT thinks of math is too human. What do I mean? If you ask ChatGPT to sum up 15 numbers, and you don't have the same number of digits or something, it'll almost always give you the wrong answer. Now, it's kind of ridiculous. This is a computer. To do the inference, that's the conversation you're having, and it's trying to add up. It's, utilizing many, many, many billions of assembly instructions, or the equivalent on a GPU.
Yeah.
Where it could do this with like 5 assembly instructions if it thought like a computer and not like a human. LLMs, large language models, were designed to process human language or process fuzzy reality sort of things. Math is not that. Like there is no fuzziness. 1 and 1 is always 2, right? There's this joke that, you go to an accountant, you ask it, how much is 1 plus 1? He says, well, how much do you need it to be? With math and physics, when you manipulate algebraic equations, there is no room for fuzziness. If you ask ChatGPT to solve a math problem, like a high school or undergrad math problem, if you just ask for the solution, the chance of getting an error is much greater than if you ask it to detail all the steps along the way. That's very human thinking.
Mm-hmm.
When we train in universities, when we train, people coming out of high school and we take them through undergrad and graduate studies and PhD, we train them that in certain things, you should not think like a human. You should try and think like a computer.
Mm-hmm.
Because the way, if you have a set of equations, the decision, what step to take, is perhaps based on intuition and experience. But once you decide that I'll move the variables from, the left side to the right side, there's only one correct way to do that. There is there's no wiggle room. And trying to get, and even in high school, elementary school, we teach kids to do arithmetic. But when they get to high school, we say, no, don't do arithmetic by hand. It takes too much time and you're more likely to make mistakes. This is a calculator. Use a calculator. And right now, the main approach is there's this shiny new hammer, these LLMs, and they do wonderful things. But not everything is a nail.
Mm-hmm.
And Qruise is going in a direction of, okay, if not everything is a nail, what's next? And we have some ideas, but not quite yet ready to speak about it publicly.
Mm-hmm. But maybe we can segue to Qruise then and speak generally about the kinds of problems you're solving with that framework.
Yeah.
Would you just like to give a quick high-level pitch sort of what Qruise does, and then we'll get into some more details?
Right. So Qruise is developing essentially machine learning physicists. Right. If I said earlier that right now language models aren't very good at math and physics, we believe we know why. And the long-term goal is to help people in development labs that develop kind of new sort of devices by having like an infinite number of junior physicists working with them 24/7. Now, we're not going to replace the more senior people anytime soon, and just having a lot of junior people in software doesn't solve all the problems. Like there's this kind of 1,000 monkeys on 1,000 keyboards don't generate Shakespeare. And you can't take 1,000 PhD students and tell them, build me a quantum computer. You need somebody with more experience to guide them. So the software won't be able to replace the more senior kind of judgment and strategy. But the day-to-day, a lot of it can be done by software, by machine learning. And what we're focusing right now is what's known as this inverse problem of, okay, I've built something, it doesn't quite work the way I planned. Now I need to understand why.
Mm-hmm.
And we originally built the software very much for quantum technology, but it turns out it's a little bit like, Amazon started building a bookstore.
Mm-hmm.
But once they had, the web infrastructure and fulfillment and logistics and all that stuff worked out, they realized that, hey, I can actually use it almost directly for selling absolutely everything else.
Mm-hmm.
And we kind of started out trying to provide algorithms to help quantum computers work better and understand why they're not perfect. And it turns out that if you replace the simulation from Schrödinger equation to, I don't know, Maxwell equations, then suddenly you can solve very similar problems in many other fields, fluid mechanics or whatever it is, because the methodology and ideas that sit on top of the simulation don't really care what's inside the simulation. They're quite general. So the way we train physicists to kind of think about how do you analyze data to figure out what's going on, this methodology is quite general, not very dependent on which subfield of physics you're at. Right? And the equivalent algorithms are similarly not very dependent on the field. Of course, you need to have, let's say, a very reliable simulation in whatever field you do. But I'll give you an example. Let's say I have a model of a system, and I optimized it to be as close as possible to the data, but one of the parameters in the model of the system still has a very big uncertainty. Why? Because my data doesn't include sufficient information to kind of narrow down the uncertainty. You can ask the computer to design a set of experiments that once executed will give you information that once analyzed can narrow this uncertainty of this parameter, which is extremely useful and important. But all these algorithms don't really care what sort of physics there is. All they need is that they need a simulation, and they need the simulation to have certain mathematical properties. But once you have that, you can do what's known as Bayesian experiment design in almost any field of physics.
So if I understand that correctly, you're saying essentially that you would develop an algorithm that identifies not only if a system is underfitted, let's say, but also what the root cause, like where you would most likely find the root cause of that underfitting, where this model would need additional parameterization in order to fit the data in a good way. Is that roughly the right way of thinking about it?
So there are two issues here.
Okay.
One is my model is too simplistic. It doesn't include the right physical phenomena. It's missing some parameters. And I need to figure out what to add to the model. This, at the moment, is beyond the capabilities to do automatically. Okay. This is where you need kind of physical intuition, etc., and experience. And that's really hard. But let's say you have a model that actually, doesn't do a very bad job, but you still want to know the value of certain parameters to high accuracy, but you haven't collected the right data. You want the computer to figure out what's the right data to collect so that you can narrow down these parameters. So this we can do automatically. The part of trying to figure out what to add to the model, we don't have a very smart way of doing it. So we can just try shit, throw stuff against the wall, see what sticks, right? If it's a computer, it can throw things really fast. So maybe you can make some progress this way. But that's kind of a brute force approach to things. And we have ideas of a more refined approach, but we're not there yet.
Okay. When we talk about this being generalizable as well, I don't want to dig in too much into the details of what fields it would be generalizable towards, but just in terms of where you're coming from when you're saying it, do you mean that it's generalizable across, let's say, architectures? I would assume these kinds of approaches are, but it's even more fundamentally than that, perhaps. Yeah.
So, okay. So we came from quantum computing and quantum sensing, and our academic background is control of these types of systems. So we had to deal with very different systems, right? From room temperature envy centers to millikelvin superconducting systems, and also time scales that vary from the nanosecond to the microsecond to the millisecond to the. This kind of forced us to create approaches that are actually very flexible. Because although we were dealing with always things that fall under the kind of headline of quantum computing or quantum technology, kind of if you kind of look down into the detail, they're actually very different from each other. So kind of that led us to seek approaches that are general and are not very specific to the physics. And once we developed them for quantum, we realized that, hey, we made something that's actually even more flexible than we realized. But the flexibility stems from the fact that over the last, for me, 15 years, for some of the professors, it's more like 25, they've been dealing with a wide range of physical systems. All of them still under the title of, quantum technology, but they're very different. So we had no choice but to develop flexible approaches that aren't too specific to the architecture or to the type of system, right? Mm-hmm. When you're trying to optimize a quantum gate, you're looking for ways to do it that'll work no matter if it's envy center or trapped ion or superconducting. Mm-hmm. And you end up with this kind of flexible approach that's actually even more flexible than you thought. And you can take it into other places.
Okay. One consideration when it comes to this offering and another initiative that you've been involved in. So I know you've been involved in OpenSuperQ. I think that's now actually evolved to OpenSuperQPlus these days. I don't know if you're still part of that project. Maybe we can start. Yeah, maybe we can start there.
OpenSuperQPlus, yeah.
Okay, so are you able to use these technologies now that you've developed as part of Qruise actually in that?
So the kind of the story of Qruise is kind of intimately tied to OpenSuperQ and OpenSuperQPlus.
Okay.
Not more the original OpenSuperQ. So we actually started as an academic open source project known as Qruise, that was developed as part of OpenSuperQ. Right? We needed to provide control algorithms and these sort of things for OpenSuperQ, and that's how we created not the methodology. The methodologies predated that, but the software. And then we created Qruise, the company. We essentially forked the open source project and continue developing it as proprietary. Mm-hmm. Because it was MIT license and we could do that.
Okay. And just then to help people with putting the inventions into context now, in the OpenSuperQ project, what are you actually doing that requires the involvement of the Qruise products? If you just want to paint a picture of like what the target of that project is and how that's being facilitated.
Okay, so the idea was that, okay, you have this quantum computer, every qubit is slightly different, and a priori you don't even know the exact parameters of the qubit. And yet you want to to create the same gates, the same operations, and they on all the qubits, and they have to be very, very accurate, right? But so you're trying to do is essentially, having kind of, think of it as, you get a set of very different cars with different steering, different tires, different, I don't know what engines.
Mhm.
And they need to kind of traverse this really complex path. And they need to do it exactly the same to the millimeter. But they're all slightly different. I mean, they're all cars, but they're all slightly different. And we had to build algorithms that'll, be able to do that, be able to understand quickly kind of the particular parameters of each qubit, each car, and then figure out how do we need to tweak the driving, which superconducting qubits are driven by electromagnetic fields in the gigahertz range, which is
Mhm.
are known as microwaves. Right, the microwave you have like at home is like 2.4 gigahertz or something thereabouts, which is why when Wi-Fi was 2.4 gigahertz, it failed when the microwave was on because they're basically using the same frequencies. So superconducting qubits are driven by microwaves, typically not as low as 2.4, more like 5, 6, 7, 8 gigahertz, but something like that nature. So we needed to figure out how to drive the qubits very precisely and to tailor it for each qubit in each device. And if you
Mhm.
heated up the chip and cooled it down again, you needed to do a do-over because the engines are now different and the tires are now different. It's still the same car, but it's not
Mhm.
exactly the same car, and you need to kind of fine tune everything again. And that was the role of our team.
Okay. How would you say the resources for a project like that compared to some of the other players in the space? Like one of the considerations I have is I would assume that, like for example, the development of machine learning models, it's quite resource intensive, and the players that have large budgets that they're able to allocate to these kinds of projects are able to get a long way, especially when it comes to scaling up the system. So like the largest superconducting quantum computers come from like Google, IBM, these kinds of players. How well budgeted would you say the project was from the perspective of actually driving this kind of innovation, and how far would you say you've come so far in that project?
So I think that's the wrong question.
You can correct it if you want.
In 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 Europe, we're trying to compete with the big commercial companies with university-led projects.
Mhm.
And building a 100-qubit quantum computer is a huge engineering feat, and one to which universities are not well suited, in my mind. If I were kind of in charge of project funding, instead of giving 50 to 100 million to a project to build a big quantum computer, I would give 10 million or 5 million to a bunch of universities and tell them to look for better qubits, to
Mhm.
build the best 10 qubit chip possible, and then patent it, through it from Sunday, and then create a commercial company to scale it up. The so first, yeah, the budget you get in universities isn't as large, but there are other issues. European approach is to distribute, to have everything distributed, multiple countries, multiple universities, etc. These things benefit from a concentration. And in IBM, everybody working on quantum, or almost everybody, is in upstate New York, at least working on the hardware.
Mhm.
Um, it's really hard if people are at different universities and then they have different motivations and different agendas, and everybody's in multiple projects, so they have multiple priorities, and they. I would I would change the way quantum funding is done in Europe. A lot more small projects to make breakthroughs in qubit design, circuit design, gate design, that sort of thing, which is sorely needed in the field, and leave scaling up to commercial companies.
Mhm.
Because if you created, a 10 qubit chip, that has far better fidelities than anybody on the market, and you patented it, you'll have a line of VCs kind of around the block waiting to give you money.
Mm-hmm.
And on the other hand, this is the sort of thing that universities do well, kind of go very, very deep, understand everything, to the finest detail, come up with new ideas, do essentially technical proof of concept. On the other hand, there are things that universities don't do quite as well, which is kind of large projects that are, have a very significant engineering component. Mm-hmm. Now, sometimes you have no choice, right? Because if you're trying to build the LHC, then, there's no commercial side to this equation. So you have to do it in an academic environment. But here, universities in Europe are competing against commercial companies in the US.
Right.
And the skill sets are different. And the strengths are different. And we can choose our fight. And I think we're choosing the wrong fight.
Mm-hmm.
I think
Understood. So I think that leads us very well to the last question that I was going to ask you, which is specifically about what parts of research are gaining sufficient attention in your view, and which ones would require more attention and more perhaps funding on behalf of the university. So you mentioned that your opinion is that a university should focus, for example, on qubit design. But do you have any more, let's say, concrete?
Yeah, I have. But I want to maybe clarify. This is not the university's decision. It's the funding agency's decision.
Mm-hmm.
Because if the funding agencies are putting out, 200 million euros, and we're going to fund 3 collaborations to build quantum computers, we're going to give each 70 million or something, right? Then this is what the universities will do. Mm-hmm. And if the funding agency said, okay, we're going to fund now 25 programs to build better qubits, and it's small, it's like €5 million project. And you can have it everywhere, doesn't matter, but every project is localized so that people can sit and work together. I think overall you'll get better results, but it's not the university's choice, it's the funding agency choice. Mm-hmm. That's one. Another thing is that you ask what's not covered well, and I think machine learning. A person today can finish a PhD in quantum physics, work on building quantum computers, and never take a single course in machine learning. I think in 2023 that's insane. I think machine learning is clearly becoming a very basic tool, right? You don't need to develop new approaches in machine learning. But just like you can't really do, let's say, quantum technology without knowing how to program, you can't do quantum technology without properly understanding the tools that machine learning make available, and the approaches that machine learning make available, right? You don't need to design new neural nets, but you do need to know how to kind of utilize existing architectures in an effective way. And most, okay, I don't know if most, but probably most people finishing PhD in quantum technology, don't go through machine learning training. Mm-hmm. And I think that's a big mistake.
Mm-hmm. Good. So then, more resources to machine learning, or more prioritization perhaps towards machine learning at least. We're over time now, and I think we should cut it here. I really enjoyed having the discussion, Shai, so thanks a lot for that. Yeah, I hope you have a great rest of your evening.
You too.